Okay, so thank you for coming this afternoon. So for this session, I'd like to talk about incentive design for commercial industrial loads, in particular as applied to the problem of interruptible loads. So, well, I guess everyone is familiar with the interruptible load program. It's voluntary. It's part of demand-side management that allows the customers, especially large customers, to operate their generating units and reduce electricity that is drawn from the grid, in particular during intervals where you have a deficiency in supply. Okay. So it's more as a voluntary action by the customers to reduce their power consumptions. Historically, it was promulgated under the ERC resolutions, and it's presently open to non-contestable customers, contestable customers, and locators in economic zones, free ports, and also those that are directly connected to the transmission network. So you therefore have a combination of customers that are connected to the DUs, and also customers that are directly connected to the transmission network. Now, the main application of this program is to request large customers to deload whenever the system operator issues a red alert notice. So, just a review, I guess, the red alert is due to any one of these possible conditions. Could be a contingency reserve being zero, generation deficiency is existing, which is mostly the main reason. There's a critical loading in some of the equipment, could be transformers, transmission lines, other equipment, and also imminent overloading of transmission lines, probably in the next few intervals. So whenever there's such a notice from the system operator, then interruptible load can be called on to supply the necessary backup power. Now, recently there was a recomputation or redefinition, I guess, of the compensation that can be provided by provided to those customers that are voluntarily deloading. So it's a combination of course, reimbursing the customer for their operational expenses for fuel, I guess. And in addition, they are also reimbursed for maintenance costs, and mainly, I guess, maintenance costs to run or operate their backup generators. So here in this formula shown here is there's a value given for what we call this, the fuel consumption rate, which is 0.34. I guess this was increased from a previous value of 28 liters, 0.28 liters per kilowatt hours. And there's also, of course, the high dependence on the compensable kilowatt hours, which is normally measured using the existing meters, I guess, of the utility. So, in addition, of course, to the maintenance cost that is added to this compensation. So, it's more or less a simple formula, easy to understand, and however, probably you may have some objections to the values that are given here, and what are the factors that go into the computation of the deloading compensation. So we say this is just merely fuel cost, is this merely operating costs, and is there no other factor that has to be included in the computation of this compensation for these customers? Now, we go back, I guess, to what is the interruptible load program. That normally these are targeted to large customers, normally about greater than 1 megawatt. Of course, later on this could be reduced to a lower value. And obviously, due to the requirement that has to be a large customer, the number of participants could be limited to a few customers. Now, in other utilities like was mentioned here, San Diego, gas and electricity, I guess, they allow the 50 megawatt customers to participate, I guess. So at this point, however, in the Philippines, most participants are those that have a sizable amount of loads. Of course, you already mentioned that the main cost component of this program would be the generators operating instead of drawing power from the grid. And these generators have what we call as low capital cost, but they have high operating costs due to the maintenance that you have to put into the generator in order to make them available at any given time. Make them highly reliable. Now, there's also an idea of using these generators to preempt possible interruptions. However, there's a counter argument that maybe this would contribute to more pollution. So therefore, I guess a longer operation of these generators as a more or less a generator, purely a generator, not just a backup generator, but as a generating unit, also could be counteracted by the effect on pollution. But I guess this is one of the considerations probably in the future, that we're just using these generators for backup or for interruptible load programs, but you could actually contract them to supply power in the future as a generator. Now, the main idea or question being put forward in this session, however, is the question of incentives. Okay, how do we incentivize these customers to participate? Now, if you look at the list given by Meralco, I guess they have a large number of customers that have enlisted. And I guess in the past, some of these have been called on to provide interruptible load during the red alert conditions. Now, in order to interrupt the loads, normally these customers are given various incentives, like lower electricity bills, and as well as additional incentives that are probably given or provided on a case-to-case basis, at least in other jurisdictions. Normally, since these are large customers, as mentioned here, normally the implementation is through a bilateral contract. Yeah? So large quantities of energy that have to be contracted, therefore a contract has to be drawn up. And in addition to the contract, to payments, I guess, to these customers are also the associated penalties that could be imposed if you have a non-performance. Now, other incentives that have been mentioned in other jurisdictions are capacity credits, for example, or capacity credit plus rate, use of strike price, per event credit. So these are some of the ideas that can be included in incentivizing these customers to participate. We already mentioned the associated penalties, I guess, that due to the large amount of energy that are being used up. In literature, there are a number of incentive payment designs that have been proposed, and this is just one of the many that have been proposed in the past. Most common are the pay-as-you-go method. These are therefore classifications where the customer receives compensation per unit of interrupted load. So these are normally done ex post. So compensation is provided after the interruption, the actual interruption is provided. Okay. So, and the alternative is the pay in advance, where the utility provides the customer with a compensation. It's much like the reserve payment that we normally provide to our reserve generation we provide a certain guarantee of or incentive in advance of the actual load interruption. So whether they are actually implemented or not, we already pay them in advance for these possible interruptible loads. So these are therefore the two types of incentives that, or general classifications of available incentives. Now, of course, there are certain limitations to the applicability of these methods. A number of limitations are mentioned in the literature, like load curtailment, in the limitations in the customer's amount of load that they can curtail, probability distribution about the load of the customer itself. So it's not, customers normally have a time varying load, and therefore you cannot really expect them to be curtailing a large amount all the time. So there's a probabilistic nature to the load of the customers. And also in some jurisdictions, the dependence of the price on wholesale electricity markets makes it heavily dependent also on the probability distribution of the electricity market. So in particular, if you have a price, what do you call this, a market scenario. So the price dynamics will heavily impact the conditions or the what do you call this, yes, the contract conditions and payments. So these are therefore some of the main what do you call this, difficulties in defining the contracts for these interruptible load generators. Well, we'll just skip. So these are just examples of formulations of the investment incentive payment design. We already mentioned before the constraints that normally are imposed. Also, in some cases, the participation, the degree of participation of customers have also to be included. I mean, if you provide them with an incentive, will they have the option to reject, or how much option do they have of rejecting the offer? Now, the bottom line is always, when drawing up any contract, is the concept of utility cost and benefits. So it's always, when you try to draw up an optimization problem, you always base it on what is the cost, what is the benefit. And always there's a big debate on what should be considered as the cost and the utility of a particular type of optimization problem. So quite important to mention is that technology is also required in this type of contracting, interruptible loads. So it's not just a no-cost type of endeavor. So additional meters may be required, and also sometimes in some cases, or like in our particular case, where there's the price of the contract is not dependent on the market price, so there's a decoupling between the per ERC formula. There's no coupling between the price that is being paid to the customer and the price that is really being bought in the electricity market. There's no such dependence. So just have a constant value. So once you have this decoupling between the actual contract price and the market price, you may end up with disincentive to customers to participate. Also, the necessity of baseline information. Okay, so whenever we go into contracting with a particular customer, you have first to come up with a baseline information about the load. And it's not, all customers are not identical, so one customer is different from the other, and if you offer the same contract to both customers, then it may be not advantageous to one, maybe advantageous to the other. So if you have a uniform contract, therefore, it may not be an incentive for more participants. So since they're paid the same, or doesn't take into account the dynamics of their load. So baseline information, therefore, is quite important. Other consideration is simplicity, of course, verifiability, accuracy. Of course, these are all, I guess, implementation requirements. Also, the possibility of gaming. Whenever you have multiple participants, customers, they may try to game the computation among themselves, I guess, to probably come up with the best result, I guess, or payback for their interruption. If you have multiple, especially if you have multiple players in the system. In conclusion, I guess the use of interruptible load must consider the diversity of the customers and also provide portfolio of options. It's not just a one uniform formula for everyone and take it or leave it. And these programs should provide customers with a choice of participation level. So can I always participate 100%, 50%, or just 10% of my total load? And of course, it should be proportional, therefore, to the incentive that these will be given. And I guess lastly, we should mention that if you give customers more control over the load reductions, they are more incentivized to participate in the interruptible load. So they can determine how much and at what time, I guess, and they have some degree of decision left to them, then they are more incentivized to participate. Thank you.
So the next presentation will be delivered by John Audie Cabrera with the title of Designing a Menu of Contracts for Demand Response of HVAC Systems.
So hello everyone. So I'm Audie. So I'm, like Sir Mike said, I'm part of another PCARI project which is entitled Resilient Cyber-Physical Systems. So the common word there would be the word resilience. So just as like their project, we also have sub-projects in our group. So, and I'm under Building Energy Management Systems, which I guess I'm basically here because there's a word in my title that echoes a lot of what Claire and Sasha has been talking about it, and that's demand response and basically contracting. And so I'm going to motivate the work with some ideas that they presented earlier. So imagine that you have a load profile, and then you have, so this is your estimated load profile for a number of residential consumers. So, and so you build power supplies that should deliver the required amount. So again, what happens if you have emergency situations wherein you have unexpected peak loads? So what you do essentially, so one solution would be build another power plant, but that's largely expensive. And also, you could also argue that you don't actually need to run all three at the same time. You just need to run that extra power plant during that critical peak period. So that goes without saying. That's hugely inefficient. So what can you do? One way of doing it is you have just plain interruptions, I guess. But that causes discomfort to your customers. So another solution would be, how do you want to shift that peak load to an off-peak time interval? So how do you implement such techniques? So you might need some kind of battery. But do we have that battery in our grid right now? And surprisingly, the answer to that question is yes. And we're actually in one big battery right now, this room. HVACs, actually heating, ventilation, aircon units have like battery-like properties. It's more of a leaky battery in that sense. It's because it's possible to store energy because of thermal capacitance in our buildings. So that just means that if I'm going to put effort now, that effort would somehow be sustained over a long period of time. And that just means that the transient response for your consumption would be relevant up to 15 to 30 minutes for typical buildings or room, essentially. So, yeah, so we could use HVACs to implement demand-side management techniques, or in this specific sense, what you call demand response. And again, I'm trying to provide the solution in a contractual framework also. So, say you have two participants in this contract, which mainly are the principal, which wants to perform, say, peak shaving. And then you have your customer, which in his mind wants to maintain his comfort, say, at around 22.5 degrees Celsius, that's his desired temperature. And he's also sensitive about his costs for consuming that. So I'm trying to formulate how do you offer a contract that would be beneficial to both objectives, essentially. And for the principal problem, it's essentially just trying to minimize that peak. And for the agent problem, so there's a variable there that's actually very important in this whole framework, and that's data over there. It's covered by that in the center in the center of the presentation. So that essentially what you have there is a parameter that describes the customer's willingness to trade off between their comfort and their desire to save money, for example. So all this framework, you have two objectives, and they're actually two contrasting objectives. So what you can do there to formulate everything in one neat optimization problem is to use design it as a Stackelberg game. It's essentially a leader-follower game. So the principal or the power utility here would be the leader. So any actions that the principal would make or decisions would have to be echoed through the to the power consumer. So power consumers may not decide things that are outside the realm of what would the power utility decide. So the power utility would offer some kind of price signal or some contract to the consumer, and he has to react accordingly to that offered contract, essentially. So yeah, I'm not going to go into details about equations. I guess that's some kind of subtle way for students to say we're not kidding around. Yeah, so this set of equations essentially describe optimality conditions for your consumer, and there comes this problem arises that given that you're a power utility and you want to contract a number of customers to perform this demand response, and you don't know how efficient they are in shifting their load, which in terms of their HVAC consumption, you don't know how likely they would change the range in their temperature, essentially. So that problem actually produces customer types, essentially. So one customer type could be someone who's not willing to change their temperature as much compared to someone who's willing to change their temperature from 20 to 25, for example. So what can you do even though you don't know which contract? So what you do is you offer actually some kind of menu of contracts. So the menu should look like this is what I would offer this type of agent, and then this another pricing structure for another type of agent, such that they choose the one that they would be that is intended for them. So again, for that to work, you have to put in some kind of participation constraints. So you want to ensure that you're going to contract you're going to contract at least one type of customer. So you need to say that by joining this demand response program, you're not going to incur more costs essentially. And then by also adding some compatibility constraints, which is basically restricting the a certain type of agent from getting or hedging the contract that's offered to another agent. So that's what you call the compatibility constraints. So, so the compatibility constraints just basically say that efficient costs, the cost for the efficient agent getting its own intended prices should be smaller than if it's going to pretend and get the prices for the inefficient one. So yeah, I'm just going to skip this. So you have your optimization problem, and going straight to how do you implement this in, say, you want to implement this contract for, say, 30 days or more than 3 months, for example. And so the solution here is actually just calculated for a single typical day. But if nothing really changes that much, say your load profiles don't really change that much, whether it's kind of the same season, the solution here should be, solution for only a single day should suffice to be used for, say, that 30-day contract period. But then again, in the model itself, you're really accounting for stochasticity or randomness of what would happen in different weather scenarios, for example. So you have to incorporate that in the optimization problem. And also another thing would be, in the model, certainly occupants provide a lot of heating load to the HVAC. So that's also one thing that's kind of stochastic in nature. So, but as of the moment, it's not yet, it's not approximated, it's just estimated. So what I've done is use past weather scenarios to produce, to approximate essentially a solution that would be robust to, say, a longer time period of contract. So this is the results for the contract itself. So external heating load there with a bunch of lines there. It's essentially the scenarios that you would encounter for a 30-day period contract. That's that's supposed to be your historical weather data. And then temperature there, it's not that apparent, but the red line there is supposed to be, that's the trajectory for an efficient agent. And the yellow line there is for the inefficient one, which just means that, yeah, for the efficient one, it produces wider changes in its temperature, especially during the peak hours. And I designated that to be from, say, 8 to 12, and then from 6 to 10 in the nighttime. And this, by doing that, what happens in the control of the HVAC is you offload the consumption to an off-peak period, and then you reduce your consumption during the peak period. And the efficient agent essentially produces a more aggressive control compared to an inefficient one. And in terms of load profile, yeah, so the efficient agent is able to reduce peak consumption than the inefficient one. But this is the sample contract. So say you want to implement time of use pricing, which is basically you have a price for peak and then off-peak period. So this is essentially the menu that you're going to offer. So you're going to say that during the peak price, I will offer, if you are willing to change your temperature from 21 to 25 degrees, I'm going to price you this way. If you're willing to just change it by just about 2 degrees, I'm going to price you this way. So that's basically a rough format of the contract. And then this results say that by doing stochastic optimization, by incorporating historical weather scenarios to your problem, it approximates better what you're going to offer in the contract, basically. So you're saying you're going to offer 25 degrees there and 21 degrees in minimum temperature. And by doing stochastic optimization, it approximates that well. You can see the red line there is the result of the contract, basically. So max temperature for efficient says I'm going to be at this temperature maximum, and then the blue ones there are the distribution during the contract period. So it's centered nicely for maximum temperature. Minimum temperature, it's kind of pessimistic in that sense that the solution says I'm going to be at 21 degrees minimum, but actually what happened in the 30-day period is above that, which is perfectly fine. You're worried more that you're going to say that I'm going to say your maximum temperature is 24, but most of the time it would be shifted. Just like if you're just going to, instead of using historical scenarios, you're just going to average your weather data. So that's basically it. So I modeled the contractual framework for HVAC consumption in a bi-level program, and it uses some fairly simplistic assumptions. For example, I just parameterized customer types to be only 2. It could be a lot more. Also, there's stochasticity itself. Just as Sasha said, no model is correct. Everything is subject to errors, essentially. So, in the model itself, in the model, you actually won't have consistently correct values for your model. So that's also another thing that I'll be looking into, and other DSM techniques also, such as say you want to minimize peak average ratio, and then under dynamic pricing framework. And so I want to end my presentation with reorienting the whole goal of this is to contribute to that paradigm shift, that how do you view energy consumption, which is as of the moment it's very bleak. You want energy now, I have to get it. So what if we can design a system that says that that I will respond to the resources that are available and essentially adapt to the conditions of that environment, and and that bleak view of say a building can be transformed into something of like a living organism such as this. So thank you.
Thank you very much, Audie. So the last 3 presentations, well, in a way, gave us an idea on the contracting, the application of contracting. So Claire was able to lay down the inspiration of the work. Allan was able to give us how can customers respond to the needs of the power system, and in particular by operating the backup generator. And Audie just told us how another way for customers to respond, and that is by adjusting their thermal load. So that would be another form of interruptible load program. Say you have utilities here, you have big shopping malls or big offices connected, or you have them as your loads. Then aside from looking at their backup generators as the only resource, why not we also look at the temperature profile as another resource and offer this contract to them so that they can respond. Now, all of this will be enabled, all of this will require constant communication between the customers and the utilities. And I am now leading towards the next presentation, which will be delivered by Dr. Nestor Tiglao, and he will talk about transactive energy. Nestor?
Thank you, Mike. So I'm really glad that I'm the last speaker in this session, because the previous talks sort of laid the foundation. of what these technologies will be capable of doing. So I will, although the general topic is transactive energy, I will discuss an actual implementation that has a lot of potential. It's called power matcher. So my background is on Internet of Things and wireless sensor networks, and all the power engineering stuff are really, it's just a review, it's sort of a review for me today. And I really am very optimistic that there's a real use case for all this technology to be used to benefit the smart grid technology. So right now we're seeing a lot of social networking that's driving the evolution of smart devices. And we've heard the word smart mentioned in this seminar. And what this is that there's a lot of capability now to put intelligence and smartness in individual devices. So be it smart meters, be it your smartphones, even individual appliances, as I will show you later. So where are we at in terms of the internet technology and the World Wide Web? So we are actually in the Web 2.0, somewhere in the middle of this graph. But we are moving towards a Web 4.0 where you have really intelligent agents on the internet with all of those artificial intelligence, machine learning capability, and even a whole electrical network intelligent enough to respond to local changes. And instead of just one-way flow of information and power, we can have even a two-way, bidirectional flow of information, control, and energy. So DR and DER today, these technologies, these mechanisms require that we monitor all the consumption and also the renewable energy generation devices to determine, and as was mentioned before, which of the areas will be islanded or separated from the grid. And this is the interest of utility companies. However, things are changing rapidly because now there's greater consumption and greater use of renewable sources. So that electric vehicles, solar panels are being put up in homes. There's solar farms being put up in used to be lands that are not used. So how do we ensure that the electrical grid is stable? And secondly, how do we ensure that individual consumers benefit from this changing paradigm? So that we will hopefully answer those two questions. So smart grid, it was asked earlier. So there's a transition now with the use of smart meters. However, what smart grid for me is really an electrical supply network that uses digital communications technology to detect and react to local changes in electrical usage. And that has been shown a lot with all the sensor gathering and sensor analytics and all the contract building and so on. So the challenge here is really how to make this scale. So we can do it with a few meters, a few smart meters, but not millions or even billions of consumers. So that's the idea here. So how do we make it work at scale? Because right now, the ordinary messaging paradigm is publish, subscribe. So if you're familiar with Facebook, it's a publish, subscribe paradigm. So you use you publish data, and all those subscribed to that topic will get the information. However, that's really potential. There's a potential security and privacy risk there, because there's always a man-in-the-middle attack risk. Okay, and privacy has been raised earlier. So what is transactive energy? So transactive energy is using economic signals or incentives. Okay, the first two presentations, to engage all of those intelligent devices that I mentioned in the power grid. So from the consumer to the transmission system, to get the more optimal allocation of resources, hopefully the most optimal, and engage demand in ways that have not been able to, that haven't been able, we haven't been able to do before. And this is the definition of Pacific Northwest National Laboratory. I think it's part of the Department of Energy as well. So, transactive energy is basically a two-way transaction system in which electricity can be directed to where it is needed and priced accordingly. So those are the two elements there. The ability to direct the energy where they're needed and to price them accordingly. So we have to have efficient mechanisms to do that. So there's a company, or in fact a group, flexiblepower.org, if you're not familiar with them. They actually built what could be the start of transactive energy down to the consumer level. So what I'll show you is, I'll show you a video that will show, that will highlight what could be possible with transactive energy. Right, do we have audio?
Welcome to the Thompson Street in the Dutch city of Groningen, part of something special, power matching city. More and more people are generating their own energy, using, for example, solar panels and wind turbines. Farmers are converting organic waste into green gas. Every day we see more electrical vehicles that you can charge at home. This results in a completely different set of requirements for our energy system. Take the example of a highway. 3 lanes aren't sufficient during rush hour. Too many cars at the same time and you get a traffic jam. But 3 additional lanes would be very expensive and would go unused the rest of the day, which would be wasteful. So how can we set up our energy system to match these developments while maintaining current comfort levels? This is the solution. Power Matching City. Here you find the first real-life smart energy system in the world. All these houses are connected to the system. The residents enjoy the same comfort levels as before, but with one major difference. This street automatically matches the demand for power to the fluctuating supply. It sounds so logical, so simple. You may have heard of Smart Grid. With Smart Grid, we are creating the smart energy system of the future, which makes this the most advanced street in the world in terms of energy. This is how it works. You tell your smart appliances what you want. When should they be done? When should your house be warm? When should your electric vehicle be charged? The system uses this information to plan and calculate. The appliances constantly exchange information, automatically and all day long, with one guarantee. When something is supposed to be ready, it will be. But what happens in the meantime is the truly unique feature of this system. Your electric car might get charged overnight, but not between 3 and 4. You wouldn't think so, but it turns out more power is needed elsewhere at this time, which means higher prices. A dishwasher starts up at 10 in the morning because this is when the sun starts shining on your neighbor's solar panels. Then clouds cover the sun. The dishwasher stops for a while because the dishes don't need to be done until noon. A little while later, the sun comes out again and the dishwasher finishes its chore. Users in this street are very enthusiastic. Take Andre. He is saving on his energy bill by minimizing his consumption at peak times. But that is just one option, the lowest possible price. Harry has decided to use locally generated energy as much as possible, and Kim prefers to use only sustainable energy. It's simple and easy to join. Existing appliances are fitted with a small extra controller that they use to communicate with each other. And in the future, the appliances will come with these controllers built in. The more users, the more effective the system will be.
So what's the value proposition for Power Matcher? So here I just list all the value proposition that this system addresses. And basically what it does is that this system takes the desire of the user, the consumer, in terms of energy usage and matches that with the existing supply. And of course, the transactive energy has several actions. So the basic transaction is a bid. So the bid will be based on, for example, the difference of energy consumption and the renewable generation, if you have one, from the power matcher. And then all the price exchanges will be, since this is being tested right now, will be initially simulated and evaluated under real-world conditions. Okay? And then that difference will then be offered to the simulated energy market in exchange for a price at that particular time of day. And that we call that point pricing. In addition to that, a forward pricing model can also be used if you want to, for example, change the schedule based upon the projection of some weather conditions, other conditions in the network that can affect the price of electricity. So they have standardized these interfaces, and it's called the EFPI, Energy Flexibility Power Interfaces, so that it becomes a standardized interface for all the sensors in the homes or buildings. Okay. And what it does is that the power matcher offers a decentralized coordination of all the supply and demand based on control theory and basic microeconomics, supply and demand. So, and in here, the system models each and every device as an agent, so it becomes a multi-agent system. So here's an example of the framework where you have the operator operating the, for example, microgrids or an energy supplier if you're a utility, and there's an addition of an aggregator which will just aggregate all the bids. And that will be presented to the energy market. So the power matcher is somewhere in between with a standardized EFI connecting your home appliances, for example. So here's just an object diagram showing where the devices are, and they are considered as device agents. And if you aggregate all your bids, it goes to a concentrator agent. Okay? And you can scale this up to a very large number of devices and networks. So at the center is the auctioneer, which takes all the bids and considers all the prices. So you as a consumer, you can just program or choose at which price level you want to buy electricity, or if you're selling it using your renewable source, you can also specify that price. Okay, so I won't go into the background of this sort of just reiterates what I explained. But what's important here is the impact. So the impact here is that the energy trader, which can be an ordinary consumer, so that ordinary consumer becomes a prosumer, because in fact that consumer is producing energy. If he's not using his solar panel, then he has excess energy which he can sell to the grid. And then the grid operator can also maintain a concentrator that, as I mentioned, handles all the bids, and then will handle the high peak loads at the substation level. So here's a diagram showing the network with all your different devices connected to the network, and you have your e-meter. Okay. Below that, you see all the appliances that you can connect. So these are now your intelligent or smart appliances. So how do we address the problem of security and privacy? So there's actually a big initiative in the IEEE to develop standards for secure transactions over the network. And the basic protocol is called XMPP. And this XMPP is a very well-known, very popular protocol that's used in many instant messaging systems. But what is nice about XMPP is that it is extensible. And so this is, and some of the subset of the XMPP protocols will be turned over to the IEEE. So those XMPP extensions that deal with smart grid will now be turned over to the IEEE. In the IEEE, there's a standard called P1451-1-4, which is the standard that will propose new XEPs or XMPP extension protocols for instant sensor messaging. And this is a very big development because now we can be assured that all the transactions sharing the prices and the bids across the network will be secure, right? So, and here, these are the cyber considerations. If all the devices in the homes or your electric vehicles are connected to the grid, then you should be able to identify uniquely all those devices. And then you have to register them, and the owner now has the power, has the control as to which devices will be shared and which information will be shared over the network. Right, so delegating trust is very important, and now the user, the subscriber, has full control about what items to share, okay, over the network. Okay. So trust and security is being addressed. Okay. However, privacy is viewed differently around the world. Okay. So, for example, in some parts of the U.S., in the EU, smart meters are considered as infringement of privacy. Okay. However, Internet of Things technology and standards should be able to address this lack of trust and ensure that there are mechanisms to ensure security and privacy. And I will show you an example of what later on a technology that will address that problem. So here's just a sort of a big picture of transactive energy, where you have the conventional paradigm and the microgrid paradigm, and when you integrate the renewable energy generation, you now have a different paradigm wherein these grids can be connected or disconnected from the main, the larger grid, and individual users in this network can also sell and buy electricity at a price that they want. And this sort of can automate, right, those mechanisms that were considered in the optimization problems, like what price, when. Okay. So people become prosumers. Okay. This is an example of a house generating its own electricity, but then if there's excess, you can sell it back to the grid. However, we have to ensure that there's full privacy and reliable communications over the network. So here is where the power matcher comes in. So you have your power matcher system here running, and you connect all your smart devices, okay, and each one is able to talk using the XMPP protocol, okay, and this is secure, and you have full control of what you're sharing. And then to further scale it up, we need technology that would provide, similar to the database earlier mentioned by Sasha, we have to have a secure, decentralized, and distributed digital ledger for all the transactions. Because if we're dealing with bids and prices and payments and points and rebates, it has to be secure. So, and it has to run on a peer-to-peer basis, because in that way there's no central point of failure. Okay. So the blockchain technology is something very new, but this is very promising technology. And what the blockchain does is that it's like a ledger of all the transactions, and you just update that ledger and then get a copy of that ledger. So that if there's anyone wanting to circumvent the security, they will have to change all the copies of the blockchain, which is really impossible. Okay. So what are some use cases? Identity management, asset tracking, smart contracts can now be conducted over the network in a peer-to-peer manner. So just some of the conclusions here is that there's standardization going on to secure the network, and there's some technology being tested and developed and verified so that all of these transactions are secure. So if you are interested, you can look at this website. There's a link to all the standards working group. And also, if I may, if you're interested, we will have also a innovation workshop on industrial IoT for Transactive Energy, and we will discuss in more detail all of these emerging IEEE standards and transactive energy mechanisms. Thank you.
Thank you very much, Nestor. I can't believe that the slides you used were the slides that I used to use in my class. Okay, so to end the session, I guess we only have around 10 minutes for questions. May I request the speakers to please stand in front so we could answer some of the questions the audience may have. Claire, are you still there? I'm not sure if Claire's there, but we are now happy to receive questions from the audience. Questions?
I have a question. I think this one's for him, actually.
So, one of the common criticisms I've heard about giving a rebate for capping your kilowatt hours per month is that it punishes people that have been responsible about using their energy from the beginning, and it rewards the larger users for more wasteful at the beginning. So, how would you set a baseline, so to speak, so that it's fair to lower power users who've been trying to stay responsible the whole time?
Okay, with regards to, thank you for your question. With regards to setting the baseline and I guess being fair, I guess the starting point would be what will be the behavior of all consumers if no such incentives were being given. If you're an ordinary user, will you be what do you call this? Will you be paid more or if you're a what do you call this? Or if you're a large consumer, will you be paid less? So I guess the question of equality or social equality, I guess, would be more of based on, I guess, the efficiency of I would assume that the particular user should be evaluated, I guess, based on how efficient he uses the energy that he gets from the grid. So I guess different types of consumers will have varying degrees of efficiencies and therefore if you're a large user but you efficiently use it and you don't waste a large portion of what you get, then probably you should be more incentivized than if you're a user that well, wastes the energy by, I guess, installing less efficient equipment. And I guess those type of users probably should be less incentivized.
Thank you.
Any other questions from the audience? Audie, do you want to add to that, or?
So, clarifying your question again, does that mean it's like the free rider problem, right?
Exactly. So basically, let's say you have two neighbors, and one likes to turn on the AC all day and turn up the stereo and TV, and the next door neighbor is trying to be socially responsible the whole time, and then all of a sudden the utility is providing a huge rebate to the wasteful neighbor as opposed to the responsible guy.
So yeah, it's very realistic in that scenario, in that sense that I'm doing all the effort, and that other neighbor that's not doing anything also receives the benefits of the actions essentially of the responsible consumers. So in that sense, it's not really something new in that in economics essentially. So how do you price essentially? The solution to that is you price differently per se their effort. So in that sense that they're not going to essentially receive equal portions of that benefit. So if you're slightly inefficient in your responsibilities, you should receive a lower amount of rebate.
Okay.
Thank you. I have a question for Nestor. So, well, we're talking about transactive energy, and power matcher is, well, it's a specific example. What are the principles in the domain of computer networking that will enable this contracting framework, whether it's demand response close to real time, or implementing contracts that would change every month or so?
I think number one would be enforcing or having trust in the system. So enforcing privacy and security, number one, because if people do not trust the system and it's vulnerable to hacking and to the bad people, then it will ultimately fail. Secondly, it has to have the quality of service levels. And I think it was good that Matthew pointed out that they were able to achieve that precision and accuracy because they had a very high level of the standard in terms of their reference implementation. So I think that's also the challenge here. In the Internet of Things in general, we have to have very efficient and very secure and high-performing networks. And this has to be done at scale. So if it doesn't work for 100,000 people or a million people, if that fails, then it won't be successful in the long run.
So I really like your mention of trust, because I think it's sort of a crucial concept in making the grid work. One way I think about the electric grid is as a technical system that was designed in a paradigm of cooperative engagement, and making it sort of a place where competitive entities are acting is not part of the way that the technology was originally designed. So we have to bring some of that trust back into the way that different actors participate. But my question is, and I don't know if there's a good answer, just thinking out loud, how do you demonstrate trustworthiness of a of a management strategy in the system. That is, what is a ground truth that you can hold up and say to customers or to any participant in the grid, see, we're doing a good job. Nobody is stealing anything, and there is no terrible inefficiency that's being concealed somewhere behind all these numbers. How, is there some rigorous way of demonstrating trustworthiness other than that no calamitous breaches of information have happened?
Very good question. And that's why I put in there a slide on blockchain, because people in the field of security look to this as a way, a mechanism where you can independently verify all the processes that have happened in delivering the goods from the producer to the consumer. So if all of that activities are put in the ledger, and everyone updates this ledger, and built into this mechanism is trust, then you cannot change it, and you cannot deny that this activity has happened and this event has happened. For example, if there's a fault, update the blockchain, the ledger, and then you cannot deny that something has happened. So, and that's why I mentioned smart contracts, because if all of these smart contracts are built into an electronic system that's scalable and distributed and trustworthy, then we have a solution. But of course, it remains to be seen if this will work in the future. Okay.
Questions? Yes, sir.
On the high level, looking at the electric industry that we have right now, wherein the retail segment for fairly large customer is now, what do you call that, decoupled from the utility. So now retail electricity providers are now looking for customers. They can sell contracts with them. So with this new concept of blockchain and transactive energy, how will it affect the current industry? And will there be some regulatory changes in the structure of our market right now that needs to be adjusted so as to accommodate such new concept of trading energy?
Yeah, thank you very much. And I'm sure that it would require some regulatory support, because as mentioned, these utilities were built on the fact that there's only one provider of electricity, and this is highly centralized. Now it's a different paradigm where you have decentralized it, and you are relying on peer participants to do transactions peer-to-peer. So I haven't mentioned that there should be some regulatory changes that to support this, because otherwise the regulators will complain. Hey, you're overstepping your bounds. This is not allowed. You're not allowed to do this kind of bidding and this kind of mechanism. So for sure, it will require some regulatory and structural changes.
That's a difficult question to answer because, well, from experience here in the Philippines, the electricity sector and the other sectors are not really talking to each other. And what we are presenting right now are opportunities, and hey, this is what's happening outside the Philippines. And this is what we should be doing. This is the right path. So we recognize that there's a problem. For example, from the point of view of the utility, what does it take for us to move towards that direction? From our point of view, it's difficult to answer. So, well, the bottom line is, well, we have, or everybody should recognize that there is potential. We organize this seminar so that, well, it's our way of contributing towards that path, that, hey, we can do this, but we have to work together so that the researchers, the utilities, the government will see the potential benefits. So it's just a start, and I'm happy that Nestor is now is doing his research on this path. So it's a work in progress. Yes, sir.
I'd like to add something. I think in the area of interruptible loads, the contracting is with the presence of the retail electricity supplier is going to be a tripartite contract. So if previously we were thinking contracts being bilateral, two parties every time, I guess contracts could now cover multi-party agreements. It's not going to be just one party and another, two parties contracting with each other, but probably multiple parties with individual responsibilities and deliverables. So I guess that's the new paradigm that we have, since we now have multiple personalities, I guess, in the new setup.